Okay, you can start. I go down like the street. Okay, are there any questions before we get started? I hope you're enjoying this course, that you're learning good new material. So, if you don't have any questions on the past topic, we'll move on to a new topic today, which is the discussion of available power and maximum power transfers. So we learned something very interesting in the last few lectures. That is, if you have a very complicated network, a resistive network of any kind that is linear, you can replace that resistive network with something very simple. You can replace this with a much simpler circuit that looks something like this. Okay, you can also do the Norton equivalent, which is actually the same thing. You can either be this or that. Okay, to an outside person, these two circuits are indistinguishable. Okay, they wouldn't be able to tell the difference because when you hook something onto this external terminal, they behave the same, no matter what you hook onto them. Okay? But someone asked, what is the use of reducing a very complicated circuit to something that simple? Of course, the first answer is simplicity, right? Simplicity is the beauty of life. You like to make things as simple as possible. Okay? The second thing is that it makes a lot of calculations a lot simpler. Say if I ask you the question that if I were to hook a load to this circuit network, it can be hooked to this one, a resistor which is used as a load. This resistor could, for example, be your microphone or loudspeaker, and it's hooked to some electronic network. And you like your loudspeaker to play as loud as possible. What kind of resistance should your loudspeaker have? That is, if this is a source network with some independent sources of current in it, you like as much power to go into your resistive load, like your earphone, your loudspeaker. Okay? How should I design this R sub L so that maximum power has been transferred from these sources inside to that load outside? So instead of working with this rather complicated looking circuit, I work with this much simpler one, because I know that the two are equivalent to each other. So we are going to discuss this topic of maximum power transfer and available power that you can extract from this resistive network. So the problem is rather simple. After reduction to a simpler one, the question to ask is then, if I have a source of this kind, a Thevenin source with a Thevenin resistor, and then you have a load hooked onto it, and then you have a current flowing here that goes into the load, and you like the power transfer to the load to be as large as possible. Okay? The power transferred to the load, as you can see, is P load is I load, it's I load V load. Okay, it's I load V load. It can be written as I load times V load is I R load. Okay, this can be written that way. You can also write it in terms of I load can be written as V load over. So you can write it either way, in terms of V or in terms of I. Okay, it doesn't matter. And you can ask yourself, how would I maximize this? I know that if I make the resistor too small, then the voltage will be small. This is a voltage divider. Okay, there will be very little voltage drop across this resistor. So making it very small is not the solution. Okay, if I make it too large, if I make the resistor too large, most of the voltage drop is across this resistor. Would I get maximum power transfer? No, because if I make the load too large, IL becomes too small. Okay, so the correct answer is somewhere in between, not too large and not too small. So what is that optimum value? Okay, so let's work that out. So if I write out P load in terms of V load, then it's V load over RL. Okay, but I can write out V load very easily as a voltage divider. It is given by R load over R load plus R Thevenin times V Thevenin. This is just a voltage divider formula. Okay, voltage divider formula. Okay, so then I figure out that P load, if I were to change R load alone, would be R load over R load plus R Thevenin square times 1 over R load times V Thevenin. So this I cannot change in this formula. R Thevenin I cannot change because it's not available to me. I can only change R load in order to maximize this. I can do a little bit of simplification. This R load and R load square will cancel. So I have this in my simplified formula. Okay. So what should R load be in order to get maximum power transfer? You can plot this diagram. As we said before, if you change R load to try to maximize P load, when R load is too small, you can see that this is 0 over a finite number. So it must start out something like this. Okay? And then as you make R load bigger, the power will go up. But then if you make R load too large, okay, make R load too large, R load is much larger than R Thevenin. This is proportional to 1 over R load V Thevenin. If I make R load be very, very large, or tending to infinity. So eventually it has to come down. Okay? This is when R load is very large, this is when R load is very small. So the correct answer is somewhere there. So how do I find that correct answer? The correct answer is what we call the stationary point in calculus. You find the place where this curve has 0 slope. Okay, and all of us had calculus before. So in order to find the 0 slope of this expression, what do I do? Excuse me, let me push this a little bit backward. You will not hit your leg, my leg hits it all the time. Okay, so how would I find the 0 slope of this function? This is a constant, this is a constant, the only variable is that variable. I take the derivative of the power delivered to the load with respect to the only variable in the formula. Okay, I differentiate this. So this must be Vt times something. Okay, and all of you know how to differentiate ratios of two functions, right? You all remember that. And they're all at your fingertips. The numerator function divided by denominator function. And if you don't remember it in your exam, that's fine. You can always derive it. Okay? And then if you differentiate it using the chain rule, it's the n dx d inverse. And then if you do the second one, it goes minus d minus squared dt dx times n. So it is something like d squared d dn dx minus d n dd dx. Okay, you use this formula that usually you can derive at the spur of the moment, and then apply that to this equation over here. So I should have a d squared, the denominator square in the denominator, which means that I have rt to the power 4 in the denominator. And then I should have a denominator times the differentiation of the numerator. So it should be RL plus RT. This is the denominator. And when I differentiate the numerator with respect to the variable R sub L, what do I get? 1, right? So that is very simple. And then I have to minus the numerator, which is R sub L, and then the differentiation of the denominator with respect to x, because differentiation of the denominator with respect to the variable L. So I get 2 RL, right? So this is the right answer.
Plus RT.
What is that?
Chain rule.
Inside the parentheses.
Yeah, it should be plus RT.
2RL times RL.
RT.
2RL, you're right, plus RT. Okay? You're correct about that. Okay, so I can't do my calculus after many years.
Nobody can, don't worry.
So how are we supposed to?
Such a good question.
Okay, it's supposed to be much younger than I am, so that's the difference. So I guess this is my answer. And then I can simplify this. 1 over RL plus RT squared. Let me write this as this, and then this would be minus 2RL over RL plus RT cubed. Okay, so if I bring everything into the same denominator again, I get VT and then RL plus RT cubed, and then RL plus RT over here, and then minus 2RL. And then I would have something that looks like this term canceling with this term, and then I would have RT minus RL over the cube. Okay? So I would have that, and you see where the turning point is, where the stationary point is. And then this thing becomes 0 when RT equals RL. So this is quite obvious that the turning point exists or occurs at RL equals RT for max power transfer. Okay, that is a very simple thing. So RL has to be equal to RT. And then this is called matching. This concept is called matching. The load to the source resistance. Okay, you just make the load the same as your source resistance, you will have maximum power transfer. So this is something that you should learn. You should memorize. Commit this knowledge to your memory. And next time if you want to design something, make sure that you don't put a big load there, you don't put too small a load. Find out what the internal resistance of the source is. and then design your external resistance to be equal to that of the internal resistance. Okay, you have a voltage source, it always has an internal resistance. That's why you cannot get infinite current out of your voltage source. For instance, you have a battery. If you short circuit your battery, you don't get infinite current out of your battery because there's an internal resistance in your battery. Okay, and you can sort of estimate the internal resistance and decide on what your resistive load should be in order to draw maximum power. Okay, then you would find that the P optimum, okay, then would be given by this this answer, or where's this answer with RL equals RT. Okay, this optimum is given by when R load equals RT. Square Vt. Okay, and this is equal to 1 over 4 RL Vt. Okay.
Is VT squared?
So Vt, let me see.
Is it?
Yeah, there should be a square here. I'm sorry about that. There should be a square here, and there should be a square here, and that should be a square here. And that should be a square here, a square here, a square here, and a square here. Okay? Fortunately, it's just a constant. A square here, a square here. And then that should be my, this should be R7. Okay, I should make this equal to R7. Because that is a constant of the problem. Okay, so that is the maximum or optimum power I can get out of this circuit, which is given by this formula over here. So, there's a very simple example in the book. It refers to figure 218A. Okay, 218A, and asks what the maximum power transfer should be for that very simple circuit that you have in figure 218A. And that figure I redraw on the blackboard again. Current source, the 2 amp here, and then I would have something like 2Ix over here. That is for the ground here, and then there's the 2 ohms here, 1 ohm, and then in order to find the maximum power transfer, you try to find the Thevenin equivalent of this circuit. That we have worked out before. Okay, I think we worked that out to be this is equivalent to a voltage source, V Thevenin, R Thevenin. V Thevenin, anybody has a good memory?
1.2.
What?
1.2.
1.2. I think you're correct. Okay, let's check on you later on. What about R sub T? R Thevenin. I can look in the book.
I think R Thevenin is 1.2.
No, shit.
R Thevenin is 1.2.
Yeah, R Thevenin is 1.2.
R Thevenin is 1.2.
V Thevenin is 12 over 5.
R Thevenin is 1.2. You're right. V Thevenin is 2.4. We worked this out before, so we don't have to rehash this problem again. Okay? So, it's obvious what our load should be. Our load should be equal to 1.2 ohms for maximum power transfer. And then you can use this one to calculate the maximum power you can extract from this circuit. So simple as ABC. Okay? And I was assigned 1 hour for this lecture. I think.
That's it?
Section 2.5. So we can either move forward, go into op-amps, or we can move backward and rehash some of the old materials.
Rehash.
You want to rehash? Okay, rehash the old material. Some people are complaining that this course is going too slow, the advanced students. So those students will want to move forward, but some students want to move backward. So let's see how many students want to move backward. Okay, and how many students want to move forward? Okay, you are minority, so you're smart, but you're minority. So we have moved backward.
Technically.
So what question would you like to ask on some of the topics that we have already visited? Yes?
Solution also works if RL is equal to minus RT.
RL equals minus RT. What will happen then?
It'll still be a stationary point.
RL equals minus RT. So if I draw this curve, it will go like this, right?
Yeah.
If I draw this curve, and then RL equals minus RT, then are you sure that it will work? RL equals minus RT. This goes to infinity.
But it's a 0 by 0 term.
If RL equals minus RT, this becomes 0. So it's a negative number divided by 0. So it shouldn't be like this. Looks like that. Right, it goes to infinity. So that is a catastrophic point. Everything will burn up. Okay. Because you have a negative resistance. Remember what I tell you what a negative resistance is? It's something that actually can create power. Okay, you're trying to hook something that can produce power. And then there will be too much power to contend with, and then everything will be fried. Okay, that's what this diagram is showing. Okay. Okay, do you have any questions that you'd like to dwell upon for the topics we have covered? Yes, I see a raising hand there.
At the end of yesterday's lecture, you said we did a question that came up to be negative resistance, and then you said that means the circuit is active. What does that mean again?
Well, the circuit is active means that the power is not absorbed by the circuit anymore. Okay, so let's look at the resistance and the power going through a resistance, like what we have in this example, in this lecture over here. So if I have a resistor, R sub L, and then if I have a voltage drop across this resistor, and then the current that flows in this resistor, IL is equal to VL over RL. P is IL VL. Okay, so it can be written two ways, as we have done before. Okay, written in terms of I squared R, okay, which is IL squared R, okay, or in terms of VL squared over RL. In both instances, this number must be a positive number, and this number must be a positive number. And if RL is negative, it means that instead of absorbing power, this device will give out power. Okay, it will give out power back to you. And it can only happen if you have a dependent current source or dependent voltage source in your circuit. Those are idealization. Okay, we hit a lot of things under the rug when we tell you that you have a dependent current source. You never ask us, how do you make a dependent current source? You never ask a question, right? So in order to make that, you need a lot of electronic circuitry, gadgetry, and wizardry. Okay, you make this thing, and it can appear to give you negative resistance, and that actually is something that can give power back to you. There's no violation of energy conservation because of your clever electronics that's involved. You're actually drawing power from somewhere else and give the power back to the guy who hooked the resistor to your load, or hook your thing to certain electronic system. Okay, there's no violation of energy conservation there, because inside the dependent sources that you have in your textbook, there are lots of clever things that went into making them. For instance, you might have to put in transistors, you might have to put in diodes, you might have to put in all other kinds of gadgetry that you will learn in ECE 340. Okay? And then you can design resistance at gate to be negative. That's what negative resistance means. Any other questions? Yes?
Can we do some more Thevenin transformations from like circuits that have multiple current sources, including dependent ones?
That we did before. That means that I have to revisit those lectures. Let me see. So, if you have a passive network without dependent sources, then the method is rather simple. You go through several steps, and say if you have this one over here that we have done before, 1M, this circuit over here, and then this one over here, 2 volts, these are all independent sources, and then you have this one over here, and then you have this V on the outside that is available to the outside world. And then you have 4 ohms over here, and then you have 2 ohms, and then you have 4 ohms. And that's all I have, I think. So what you ask in the first instance is, if I were to replace it with the Thevenin equivalent, I should find a voltage source and a current source, not a current source, a voltage source in the resistor in such a way that the behavior of this circuit over here is exactly the same as the behavior of that circuit over there. Okay, it can be proven. And I will not prove it. I think we went through the mathematical proof of that. That these two can be made equivalent. Okay, the mathematical proof was just to hook a current source. You hook a current source to this, and then you write down the mathematical expression for this V. Okay, this is V Thevenin. You write down the mathematical expression for this V. You find that the V has to be some complicated function because it depends on what kind of circuits you have that is hidden in this resistive network. That V must be K1 Vs1 plus K2 Vs2 plus K3 Vs3 plus many more terms. And it doesn't matter. You can have as many sources as you can have, dot, 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 and represent the rest. And then you can have your current sources, R1 IS1 plus R2 IS2 plus R3 IS3 plus dot, dot, dot. That was the circuit that can be represented in this mathematical form just from the principle of linear superposition and linearity. I hope Dr. Juan Alvarez taught you this concept. Okay. Once you have this concept gotten, it doesn't matter how many sources, how many voltage sources you have, current sources, you can write in that form. And now if you add in something like a voltage source on the outside or a current source on the outside, then what you do then is to add one more term to this equation. Okay, R nu, I nu or something. Okay, I nu can represent this current source over there. Okay, these are all independent current sources that you can have in a system. Okay, so that means that this big piece here is just the voltage of the system when you have open circuit. That is, if you do not allow any current to go through this line over here, then this last term must be 0. Okay, and this must be the open circuit voltage. And hence, any voltage that I have can always be written in terms of open circuit voltage plus a linear term in I. And the linear term you can later prove to be the R Thevenin times I. Okay? So this is just that model that we have over there. That voltage is always equal to R Thevenin times I. And you can write down your Kirchhoff voltage law on this loop, and you find that this equation is automatically satisfied. When V open circuit is just V Thevenin. Okay? That equation is automatically satisfied if you invoke Kirchhoff voltage law on that loop over there. Okay, and this not necessarily be 1 amp, it can be any number of amps that goes to this current source. So a Thevenin equivalent can be mathematically proven if we accept this fact. Okay, we accept this fact. The first fact that I wrote down that follows from principle of linear superposition. Okay, so in order to find this V Thevenin, you ask the question of what happens to this voltage at this terminal if no currents can flow. Okay, that you can solve. You know how to solve this circuit. You solve for your V. So find the open circuit voltage, and this your V Thevenin. Okay. And then there is a short circuit current that you need to find. The short circuit current is obtained when you connect a short from here to here. That is the short circuit current. And then you solve this second problem and ask what the short circuit current is. And again, this is a simple network problem. Okay, you have done this in homework 1, homework 2 perhaps, and you can know how to find short circuit current. The short circuit current should be exactly the same as the short circuit current I have in this equivalent. Okay, what is the short circuit current here? What is ISC in this diagram? If I claim that these two are mathematically equivalent, if I put a short circuit current there, or I put a short there to find a short circuit current, I should also get the same short circuit current here. Okay? But this diagram is a lot simpler. And you can tell me immediately what the short circuit current is. What is it in terms of RT and VT? VT over RT, right? So once you have the short circuit current, you can figure out what RT is. So you get these two elements pinned down. Okay? And then you can also say, well, if I don't like Thevenin equivalent, I can also make a Norton equivalent. They're indistinguishable from each other. Okay? And it turns out that this is I Norton. I Norton is just equal to I short circuit. Okay? And if you open circuit this must be going to be RT completely, must be V open circuit, must be V Thevenin. So these two are related in this very simple fashion. Okay? So the rest is hard work. You have to do the algebra to solve the network problem. I wouldn't go through that with you. Okay, I just outlined the procedure. Okay, so you can find R Thevenin, V Thevenin, I Norton in this manner. But there's a third way of finding R Thevenin. What is the third way? The third way is actually to using the principle of linear superposition, saying that if I were to turn off all the sources inside this network, okay, then the first term would disappear, right? Because all these are dependent sources. If I were to turn them off, okay, the first term would disappear. Then V is just equal to minus RTI. This is called a source suppression method. Okay, that would be equivalent to putting what kind of thing here to turn off the current source? An open circuit. And what kind of thing here to turn off the voltage source? A short, right? So this would be equivalent to doing that. So in order to suppress the source in the original diagram, or in the original circuit that I've drawn over there, then I would draw a diagram that looks like this. with the source suppressed. A short circuit put there, and then I will have 4 ohms here, and then I will have 2 ohms here, and then I will have 4 ohms here. Okay, and this source suppressed should be identical to this source suppressed. Okay, so if I look at the Thevenin equivalent, okay, these two should be the same. So in order to find R Thevenin, I look into this direction with my big eye, okay, and ask me what kind of resistance I see if I look in that direction. And all of you know how to find the resistance there, right? It's a very simple circuit. 4 ohm with 4 ohm parallel connection give you 2 ohms. 2 ohms with 2 ohms give you parallel connection. What is RT that you see in there? 1, right? So you find RT to be 1 immediately. So this is another method of finding RT. Okay? Then what happens if you have dependent sources? Things get a little bit trickier, because then things are a little bit trickier, but very similar. The 3 procedures are very similar. First, find the open circuit voltage. 2, find the short circuit current. 3, find the resistance involved. But the resistance involved is a little bit trickier, because